mini symposium. I'm Mark Clayton. I'm the director of the CRS Center here at the College of Architecture at Texas A&M. These mini symposiums are a new series that we've begun where we take advantage of opportunities that fall in our laps. So we already had one that was on mass timber construction and advanced timber construction. That was kind of fortuitously, we just had some experts available at a moment and we put on a symposium. This one's similar where we just have this wonderful confluence of experts, new faculty, former faculty, other experts who came together very generously to put on this event. So I just am going to turn it over to Mehdi Farahbakhsh, and he will run the whole show. So, so thanks for being here.
Howdy. You're sleepy. I know it's after lunch. Howdy. Howdy. Great. Thank you so much and welcome. And I'm very excited today. We have a great lineup of speakers today. So I will cut my presentation very short so we have enough time for my esteemed colleagues. Absolutely. So today we have Dr. Negar Kalantar from California College of the Arts. We have Dr. Ehsan Baharlu from University of Virginia. We have Professor Benjamin Enemoser, and we have Dr. Sora Key from Texas A&M University. Thank you so much for joining us, and thank you so much for accepting to do this mini symposium. So the title for my presentation that we just open up and hand it to Negar is how we design with robotic additive manufacturing. So architectural design usually starts with an intellectual concept that designer's hand is like the printer for his mind. And it helps him to visualize, understand, develop different aspects of the idea, main idea. So napkin sketch, as one example, is a way to externalize the thoughts in the designer's head. And computational power of computers has enabled an architect to think and design in a much more complex way that was not easy or even possible before. That happens in the digital world. Robots are the extensions or medium that enable the architect to directly bring the digital entity into the physical world. If I want to summarize those in an abstract way, I can say it's about material design and fabrication. And this symposium, when we're focusing with design with robots, it's about more collaboration between human and robot in the digital and physical world. So, but what is robot? What's the definition of robot? Robot was coined in 1920 by a Czech reporter. But the history of that is way before 1920, long time before that, when people tried to either make the labor-intensive task easier or for entertainment. But there are two approaches in architectural robotics. A robot is either a medium or tool for architectural fabrication, or it's a giant machine or space for living in. We have different type of robots, different brands, different shapes, 6-axis, 14-axis, spot dog, drones, or simple task robots. I can categorize the role of robotics in architectural manufacturing into additive manufacturing, subtractive manufacturing, assembly, and pick and place. In my research, I personally focused on additive manufacturing and different aspects, as I showed you before, material design and fabrication. I can divide them into different scales as well. Micro scale, which more related to material, meso scale, and macro scale. But the relation between those is not that simple. It's not linear. It's much more complex relationship between these scales. If I will present you with 3 of projects that I have done, and I want to just show you here. One part is just about the material, where I had collaboration with architects, construction science chemists, civil engineers, and soil and crops scientists. And I had the opportunity to work with Autodesk in Autodesk Technology Center in San Francisco, where we focused on replacing concrete, which is the, let's say it's responsible for 8% of CO2 emission, and also to address the technology and material breakthroughs. Additive manufacturing has a long history. We see it here. Can I show it here? We see it here on this chart. It says 1996, but it's I have seen a movie 1960, around 50 or 60. There is a machine that is 3D printing stuff. So it's long before that, but it's more about how we can deposit material in a way that where we needed it. So in one paper, we just introduced how we can turn the backyard soil into a material that we can, or into a construction material. It's more about in situ resource utilization, where we can extract material from the site and build in remote area, extraterrestrial kind of construction or something like that. About the design part, I just want to introduce this project that when we think about the design part, our design is limited to the machine that we are using. Either we are using gantry, it's about cable robots, or a telescopic boom with a 6-axis robot mounted on it, or mobile robots. The object or the space that you can build with it is always limited to the scale or the size of the robot. Always the robot is a bit larger than the object or the building that you're making. So we propose this print-in-print strategy. It's a design approach that we can design a geometry, break it down in a way that we can nest them into each other. And that way we can build structures larger than the scale of the robot. For example, this one, there's a design criteria. Whenever in a geometry, we have different curvatures. We have positive, negative, zero curvature. But whenever the curvature of the geometry changes, something like that, it should be broken into different components. That's how, for example, on the right side, we can print this one and we can take it out. The other one, we can print it. We can bring it, print it, but we cannot take it out of the sample. Here, for example, you can see the positive formwork that we created, and then casted concrete let the formwork dissolve in water. And then when clay dries, you can easily take it off. Either you can break it down, you can pressure wash it, and then concrete's left there. And we end up with a few components that we can stack on top of each other and create a geometry. As you can see here, we have the robot, when the extruder is mounted on it, it has a limitation of, for example, let's say 70 centimeters, it's almost 2.5 feet. But the structure that we could make is much larger than that. I know I'm going so fast, so I want to my colleagues have enough time to present it. So the point is, you can break down the geometry and you can stack them, and transportation is much easier, and you can build larger structures. And your imagination would be your limitation. You can design different geometries in that design criteria. Also, design and fabrication part. When you come up with an idea, it's more educational part. I'm telling our students here that when you come up with an idea, you need to be able to design a tool. Maybe there's nothing out there. You need to design your own tool based on the material that you're using. Here you can see, for example, here, this one, we had a lot of failures, but we finally were able to make and program a extruder, something simple from here, something much more complex. In this example, you can see it was just a pneumatic system that we were able to just extrude material without any precision. Later, we had microcontroller, we programmed that, and we had much more control over the deposition process. This, what am I talking about, goes back to 2018. We didn't have access to the extruder. Probably today you can buy something online. In this project, in this paper that we have two papers, one in Acadia, was published in Acadia, the other one is under review in Automation in Construction. We were trying to focus on the binding between layers. And when we try to address that by design and technical considerations in the design process. We came up with a workflow that covers design, fabrication, and then we needed to test that with digital kind of tools we had, and also finite element analysis. And then we needed to break those physical components. So I came up with defining 8 process parameters. 3 of them were manipulating during the experiments. And you can see here, for example, on the right, you have normal layering, and on the left is where you constantly changing one of the process parameters. So we hypothesized this left one will increase the bond strength between layers, horizontal layers. That's good so far. So we needed to test that part. I'll go fast. This video is much longer than that. We came up with different patterns by changing those parameters, and we applied them into different scales. That meso scale was applied to the macro scale, and you can see the details here. And you guys are lucky here because you have access to a lot of infrastructures. For example, this machine is located in petroleum department, and you can just go there and use it for the research purpose. So we analyzed those samples in the machine with the X-ray machine and MRI machine to see how the bond strengths between those layers work. And then we used finite element analysis, COMSOL in this case, to analyze those results. We made a library that can be, with all those parameters, that can be used by a designer or AI if they want to use those features or predict the behavior of the material and the print process. And later, to calibrate those results in the digital environment, we printed them physically and broke those samples to see what's the result and get the flexural strength of the bond strength between layers. And the result you can see here, the left one is normal layering, and the second one, when you change the deposition parameter, you can see the bond changes. The bond between layer changes, or this one, which is another variable. And this is the result. For example, this is the normal layering, and these are other results. As you can see, we were able, by testing 95 samples, we were able to improve the bond strength between those parameters by 41%. But these are very detailed about technical. You saw something about the material, you saw something about the design, and you saw something about design and technical aspects of it. I have applied my research into the courses that I co-taught and taught with my colleagues here. Probably you have seen this one over there by the staircase. And this one was installed in front of Francis Hall for a few months. And next one, it should be still there. It should be still in Francis Hall in the lobby. And thank you so much. By that, I want to hand it to my colleague, Negar.
Okay. Hi, everyone. And thanks for
I'm so sorry. I just want to introduce you.
Okay, go ahead.
Dr. Negar Kalantar is an associate professor of architecture and co-director of Digital Craft Lab at California College of the Arts in San Francisco. Her research in additive manufacturing, robotic construction, transformable design, and advanced geometries and materials has been awarded by National Science Foundation. By bringing together digital and analog fabrication workflows across scales, her interdisciplinary research practice broadly how to bridge the recent advancements in additive manufacturing technologies with larger scale structures. Negar, let me stop my screen. Yes, I guess you're good.
Okay. Hi, everyone. Thank you so much for having me. Thank you, Mehdi, for the invitation and, introduction. I'm gonna start my presentation. Do you see my screen, Mehdi? Can you confirm?
Yes, we can see your screen.
And, okay, maybe do you want to stop my video or it's working?
It's working for now. I will let you know if we need to turn it off.
Hopefully you can hear me more clear. Okay. So Mehdi already introduced me, but I want to say that, I'm educated to be an architect, but I've been really interested in the topics of robotics, material system, adaptive design, performative 3D printing, and nowadays I'm working on green tech innovation in Bay Area, and a lot of plugin development for fabrications. And I've worked on a wide range of nationally funded projects in and design application and research application and innovation in the practice now. I want to start from this in talking about that how much we're lucky to live in this day, that we have these 4 components of the thing that make us to be more innovative, but not just in a design process, but in application and real world as well. We have access to the new computational design method for a few decades. We could imagine, simulate things. We have, advancement in the material. We have a lot of, knowledge about bio-inspired approaches. But I think the missing component was the additive manufacturing or advancement in the digital manufacturing. And that's the part that I think makes this look complete. But there is a big change between the way that we design. In a previous, in a conventional method of thinking, fabrication or construction is a post-process. And the way that we bring those, limitation to the design usually happen by codes and standards, because it's very conventional that we know the limits of how we can construct things. But in a new way of thinking, I'm talking about, for example, additive or robotic, fabrication and construction going to inform your design process. You cannot finish your design and come back and think about that, okay, how I'm going to fabricate it. You need to know the limitation of your tools. You need to know about, what you're dealing with. So I can see that, even if you're not the person that you're running the tools, you are the person to decide about that, is it going to be fabricatable or not. So it's really important to have this knowledge at your hand, in the design process. So if you want to talk about the robotic 3D printing and construction, there are 4 aspects that I think we should take care of it. One is material design, hardware and software, and the other one is the logistics. Is the part that, dealing with the codes and how we can change the codes for construction, 3D printing, building. And today, I want to talk about the first 3 and talk about some example of those projects. About the material, while I was teaching at Texas A&M, I was collaborating with a few other colleagues who got the X grant from the president funding about the advancement of material for 3D printing. And as Mehdi has talked about it, how we can replace it. But before starting that one, I want to talk about that, when we are talking about design with the material or designing the material, in the scale that we are dealing with, material engineer can manipulate the material in a micro scale that we are not able. So adding a new material to the template of, architects, it's one aspect, but we can work with the geometry, and computational geometry can make the performance of the material better, and we can manipulate that one. But I think the major thing's going to happen when during the fabrication, you can change the material behavior. And that's really important. For example, how you can make a material that is rigid, flexible, the material that is, solid, make it, transparent, or so you can manipulate the material property because you have this, privilege of controlling the fabrication process. So with that in your mind, this is the project that we started in 2018. We got the funding, and the process was, there are a lot of structure in natures that, for example, the termite, by adding a little, chemical from their body to the mixture of the clay, they make these large structures that are a few meters. And a lot of animals has the same thing, but it's more about, what they get from the location and how much chemical they added to it. So that was the project that we work with, material engineering. Mehdi was involved with that one, and we wanted to have the in situ material for clay 3D printing. And in a hardware, it's not just thinking about that, developing the material. When we are dealing with cement printing or clay printing or any type of paste printing, there is some limitation about the technology, and it doesn't come just for the technologies, comes from the material limitation. For example, clay is a live material, and while you're designing something that's completely perfect. The geometry is completely perfect, but when you go on a site fabrication, you're dealing with uncertainty and you're dealing with imperfection. So while we are, for example, while you're printing a clay or cement, the previous layer is not going to be perfectly as you can imagine. It can, shrink, it can have a crack, or the previous layer could, has, defect on that gonna, expose itself in a next layer. So how we can deal with that one? We were working with the ETH team group and a few people from Texas A&M on how we can, have the vision and have the sensor on the head of the robot. And we were just checking the z-axis of the robot to think about that if there is any failure or shrinkage on a previous layer, how we can compensate it in the upper layer. So we were just using 1D laser to monitor the previous layer. And it was the whole, process of developing the hardware and putting them together. And the whole idea was dealing with a substrate that you don't know what is the substrate. So for example, we didn't know that what is the, geometry under the robot. And but we know that we want to project this 2D, geometry on the top of that. So by, reading the z-axis on the process of, printing, we could adjust the head of the robot. And, it could be because of dealing with the substrate that we don't know the geometry, or dealing with the previous layer that we don't know the quality of that one. So that was, the whole process. And, we gave this, different substrate to different participants of the workshop. So each person could, develop their own, design over that. But the main thing that I think is really important, and most of us that we are here, we are designers. And a lot of things that we see nowadays in the design, we replicate the same thing that we can construct with the previous construction method, and we want to produce the same thing. But there are a few questions that we had in our mind when we do this project was how much we can make our 3D printer bigger. We cannot, go to, I don't know, few story building 3D printer. So we are dealing with the smaller, tools, how we can make the bigger building or items out of the smaller tools. And the other one is printing non-planar, surfaces without support. That Mehdi's research was dealing with that, and he shared a lot of those, and I'm gonna covering some part of that as well. In the design process, we were working on the two techniques of print in print and print on print, and we developed a technique of fabrication called nesting. And the goal was how we can construct complex form with less material waste and production and transportation costs and the storage. So there are these three techniques that I'm going to briefly talk about it. And the reason that I'm sharing this, it means that when you have a new tools or you have a new way of working with the new tools, you can generate a new way of thinking for your design process. So 2D nesting, or the whole idea of nesting, is how we break the overall geometry to the smaller components, elements that they nest inside each other. So we have a smaller tools for fabricating larger things. And so we have, we can almost produce any type of complex surfaces through the stack of material, instead of dealing with the, printing a large scale 3D dimensional surfaces. The 2D nesting, you have heard that word. It's a very common, process in fabrication, that how you nest the items next to each other to minimize the waste. But while we are talking about nesting, it's not that much. It's more about that how, the front of this first layer, the front of the second layer is the back of the first layer. So then you can, with one cut, you're cutting, two sides of two pieces. And that's gonna, reduce a lot of the cutting time and, a lot of waste in the material. And you can break the overall geometry to the smaller components or segments that could be produced from this method and through the, the size of the material that you have. So, we have seen this, for example, this type of structure, but most of them are generating from a lot of waste. So how we can, make them minimize with the waste. And in a 2.5D nesting is more about that how the overall geometry can be break that could be fitted inside each other. Mehdi showed some example of that one, but it's more about that in the process of thickening of the geometry, you have the control of this one. So it means that the outer shell of the second component is the inner shell of the first component, so they can fit inside each other. And we are dealing with closed geometry and open geometry. Closed geometry has its own limitation, as Mehdi explained about that. We need to have enough slope so we can have enough thickness for the material. But while you're, it has its own limitation, it has a lot of possibilities. For example, dealing with this complex surfaces, it can come out of one stack of material. And any place that the curvature of your overall geometry is changing, you have to break it down to the different stack of material. And for example, for that form, we could generate it from a 4 stack of material. So the technique was explored in one of the studio that we had in advanced studio at CCA. And it was about, robotically how we can produce the biome in the cities called city tree, that we can grow plants on top of that, and in a location that we cannot, grow trees and wait for 30 years, or even we don't have, soil for doing that one. So that was, how we can use robotically produce, but really, compact and ship the, the components and assemble it on the side. In an open geometry, we're dealing, we have more freedom of the design, so you can deal with more complex surfaces. And if you're interested in learning about this, we published in this year Arcadia, and we talked about the techniques, but it's more about that how you break the overall geometry to the segments that you can design the components. So I'm gonna go faster. So in a 3D nesting, we are dealing with, we have more freedom, and we are not just dealing with, think about that you have this one stack of material, and depends on the direction of your cut and the angle of your cut, you can almost produce any bend, twist, and all the variation of this typologies of the forms. So it's more about establishing a language for dealing with the, for example, robotic cut or 3D printing, that, how you can produce, an overall form with no waste during fabrication. So any type of geometry, when you know the language, you can go back and break the overall geometry to the components that can be stackable. In the process of fabrication, we're dealing with 2 techniques of subtractive strategy or additive strategy with robots. And in the subtractive, we're dealing with any type of, wire cutter or straight cuts. So we are dealing with the developable surface that we can cut. And so, for example, from one stack of stone, you can cut, all the components, and you generate, a complex facade system, for example. In the traditional, way of dealing with the robots, you can mill, the surface, and you produce a lot of waste. But if you're, knowing the limits of the tools, for example, dealing with hot wire or chainsaw or any type of tools that has only one linear cutter on that surface, we can revisit our design and generate, the design that for that. So this is a case study project that we did with the Texas A&M, team at Additive Technology Center in Boston, and we designed, interlocking vaulted structure that all the components came out of 2 stacks of materials. And the way that we did it was with the 1 linear cutters that was at this project was just hot wire. We cut all the components, and all the components could go back together with the same tools. We cut the interlocking joints as well, so all the pieces could go back together and rise the structure that way. So we did it without any crane or anything. We raised the structure, and as on the right side you could see that how we could put them back and ship it back to Texas A&M and have the structure over there. So it wasn't just waste, limiting the waste of material, was limiting even the shipping and the storage area as well. In additive strategies, most of this paste printing in robotic paste 3D printing, we're dealing with the straight surfaces, because we cannot have a scaffold out of the material look like cement to break it down. So it's going to be, we're dealing mainly with the straight surfaces. So I want to talk about these 2 techniques of printing, print or print on print that Mehdi covered about this one. All of them were about the nesting and 2 different techniques of print, in print or on print. So this one Mehdi covered, we printed the shell or the formwork and cast the material inside, and then take the material out. And you can almost generate any typology of form out of these techniques. But print on print is more about how we can, if you want to print this surface, it needs a lot of support system and scaffold under that. But if we break the geometry in the components, that each piece gonna be the scaffold for the next piece, and then you can separate them, then you can have more complex forms without scaffolding. For example, for printing the arch system, instead of print the arch, we print the components on a stackable piece, components, and then assemble it in the arch setting. So again, with a smaller tool, you can make a bigger, items. And the whole idea is how we can have no waste construction with the robotically, fabricated construction. And so we are working with now on a bridge structure, that how we can use the same technique of nesting and 3D printing for a bridge structure that comes out of 1 piece of materials. But it's more about for remote construction, the places that we don't have access to the advanced tools, how we can fabricate things in a compact structure, ship it on the site, and erect it in the site. So the pieces can separate it from each other, align with the post tension, and have the structure assembled. And it can be used, on a roof structure or beam structure. So it doesn't have, it's more about how we can make a geometry with no waste. So in conclusion, again, thinking about the new tools, you can have a new way of thinking in your design process. And for example, with the nesting that we developed for robotically construction, we have this, advantages of having less materials, less machining time, transportation, storage, and less tooling time as well. So with that, I want to thank you for listening to the presentation, and hopefully we can have a discussion after.